pick up from current slide. Okay. Just a couple of things first. There's, I believe it's next Tuesday. I'm not absolutely certain on this, but I believe it's next Tuesday is what they call our planning hearings. And they're supposed to be on the Birmingham campus for my department on, I believe it's Tuesday morning at 10 o'clock. That's right when my office hours are supposed to be on this campus. So if you're looking for me next Tuesday, basically between 10 and 12, not going to be here, okay? Because the hearings go an hour, then I need to be there for the beginning of the next hearing because we do some things together in between the two departments. And I've got to come back for a 12 o'clock class, so basically all the rest of the time will be spent driving back here in time for my 12 o'clock class, where I'll probably be late for, but you know, that. So, next Tuesday, office hour. Tomorrow's office hours are normal, 10 to 12, 3:30 to 5:15. Next Tuesday will be just 3:30 to 5:15. Okay. Next. I think that pretty much does it for any changes I know about for the rest of the term. However, I wanted to say this. Now, this class has been very good about getting research papers in. There's a class of, I think, 22 students now. It was 24, but 2 never showed. And of those 22, 4, 8, 14. So more than half of you have turned in your research paper. But that means there's still, 8 people who haven't turned in the research paper. You've only got 2 weekends left. Now, I wasn't sure last time, I think when we talked, whether the last day of class was the 31st of July or that was the first day of finals. Students in my last class, one of the last classes, checked it and said the last day of class is Monday the 31st, which does give us an extra day. But please don't wait and turn in your paper on the last day of class. Those who haven't yet, get them to me sometime next week if possible. If not, I will take them on the last day. Next week, you still get a bonus point. That 31st, you do not get a bonus point, okay? So if you get them to me next week, you still get the bonus point for July. So even though Monday is July, that's the last day, yes? No, actually, I'll give you a take-home test just like I've been given. Yeah, so I'll give that to you on Monday, and then you get it back to me Tuesday, Wednesday, or Thursday. I think I needed one of those 3 days. Technically, it would be Wednesday, but I'll give you an extra day if you need it. Okay. Second? Oh, I thought someone said something. Okay. The reason I'm pretty sure grades are due. I can't remember exactly when. I think there's something like Monday at noon, and so I've got to have your finals in the week before, Monday through Thursday. I was going to say I'll be on campus that Friday because that is a work day, but I've got an infusion that day, so I'm not going to be here. I'll have to be at the infusion scheduled for 8, but I have to be at the labs by 7, and they usually take all day long, so I will not be here that Friday at all. So that means I've got to have your grades, your everything in by Thursday afternoon. Okay, now before, what I need to do is find my pen. Did someone borrow a pen? Oh, here it is. I think I found it there. Let me mark the roll first, and then if A is not here yet, Nick is not here yet, Tiara is not here yet, Courtney Brooks is. You're top of the alphabet today. Okay. Raven's not here yet. Shakina is here. Now, I would think I got confused. The next class I know we're going to have labs. I'm not sure we're going to have a lab. Huh?
We did a lab for this one.
Yeah, last time, yeah. And I'm not sure we're going to get far enough along to get the lab done. I've got it ready. I don't have it. I was just going to have you write it out, but I prepared it yesterday, but I didn't have time to type it out, so now I don't need to, I guess. Okay. Courtney Humes is not. Charity's not here. Courtney Humes not here. Embry's not here. Essence is here. Ryan's not here. Larry's not here. Monique is not here, but Sasha is. Allison is. Hope I'm in the right place. Darius not here. Scarlett's not here. Will's not here. Brianna not here. Maya's not here. Maria's not here. Dakota's not here. 1, 2, 3, 4, 5. Just have enough for a women's basketball team. That's all, folks. Okay. Now you needed only X chromosomes are here. There are no Y's except me. Okay. All right. You needed what? Test 6, you said? Excuse me. Essence. Did you say test 6?
Yes.
Okay, I think I've located it. Finding a copy of it. All right, you can pass it. All right. And things are coming in too. Thank you. Okay. Thank you. Okay. I think we're ready to start. Any questions on anything we've done up till now?
Can I ask you a question about the
Sure.
paper?
Okay.
References do you need?
At least one.
Okay.
2 or more are better, but at least one. Outside. Can't
Do
be
you
the book.
need one page for one reference, or do you need a page for every reference?
Say that one more time.
Just, you said you had to have a page for one of the references.
One reference,
Just
yeah.
one?
Yeah, you don't need a page from every reference. Just pick one of the references and print me one page from that. Yeah. Okay. All right. Okay, we're in Fluids and Solids is the name of the chapter, topic, sorry. And 9.2, we just finished talking about density and pressure. And 9.3, which the slide says 9.4, but they numbered them different earlier edition, is variation of pressure with depth. So that's what we're going to start with here. And let me make sure that is the first slide. Oh yeah, this is the place I remember now. The old slides, the old organization of the chapter is very different from the new. So I'm finding my way through here, following the book, but that means I have to go back and forth in the slide set to do it. So there will be a little bit of monkeying around later. Okay. So 9.3, variation of pressure with depth. If a fluid is at rest in a container, like in your cup or something like that, your cup, okay, at rest in a container, all the portions of the fluid must be in static equilibrium. There is really no reason for them to be moving around, right? Static equilibrium. All points at, certainly molecules always move around, but that's just random motion. All points at the same depth must be at the same pressure. If they weren't, they would move relative to the pressure, okay? Otherwise, the fluid would not be in equilibrium. So the fluid would flow from the higher pressure region to the lower pressure region within that layer, okay? However, at different layers, they're at different depths, and the reason for that is you got more weight on top of this layer than you do on top of this layer, because there's just less stuff, more stuff over it, less stuff on the second one, okay? So, a showing of pressure with depth, the A part of this figure is not showing up here. In a static fluid, all the points at the same depth are at the same pressure, so the force F1 must equal F2. That's if you had just an incremental sheet, okay, going across there. Everything would be at the same pressure. However, if you have a larger body like this one, the pressure at the top, or the force at the top, is the weight of this water. The force at the bottom is the weight of this water, okay? And weight is pressure times area, and that would be there's greater pressure down here, assuming the same area, the lesser pressure up here, more here. Now, we also have the mass of the block, this force is downward here, okay? The difference in pressure is due to this difference in height. Nothing, so to speak, to do with the mass of the block itself. Examine the darker region assumed to be the fluid. Wait. To be a fluid, okay. So I assume they mean the darker region is here. Well, this is a well-defined fluid stuck within that fluid, it appears. It has a cross-sectional area of A, and it extends to a depth h below the surface. Okay. I'm not really clear what surface they're talking about here. That three external forces act on that region. Okay. All right. Three external forces. There's the force downward here, upward here, and downward there. That's what they're showing here. Now they're not showing any lateral forces because all those are equal, okay? Except they're balanced by exactly opposite force on the other side. But these would be the three external forces that we're seeing here. Now, wow, I just left it. Those three, because it's in static equilibrium, the sum of the three would have to go to 0, okay? So that would be, and for some reason they start with this one, I guess since it's up. Let me get my pen color changed. That would give you P2A minus P1A minus mg would equal to 0. Now you could have done it the other way. Since it's equal to 0, you could just move the things to the other side of the equation. Now, I kind of find it a little problematic that they show this as being a vector, as indeed it is. That's the weight vector, mass times acceleration due to gravity. But if you're going to do that, you really need to show these as vectors too, and that's a pressure, which is force per unit area, and the force is a vector. So if you're going to show the vector here, they really should show it there too. So I wrote it without the vector, so you're one-dimensional, everything's in the same dimension, up and down. So I just left those off rather than putting them in. But it's sort of a little bit bothering to me. They put one as a vector, but all three are vectors. Okay, is that all they had to do on that? Okay. Now, another way you can express this mass, as we saw earlier, mass density is equal to mass per unit volume. So if you knew the volume of that fluid, then we could substitute the mass is equal to rho times the volume. Remember, rho looks like a P, but that's a rho. That's the Greek letter rho. These are P's for pressure, okay? Now, if you plug that in here, you would have P2A minus P1A minus rho VG is equal to 0. Okay? And one advantage of doing that, since you're dealing with areas anyway, that gives you volume. Those are really closely related. Okay? So what you can do then with that is, oh, and by the way, I sort of skipped a step here. The volume, I should have done this first, is the area, okay, that same area of the bases up and down, times the difference in Y2 and Y1. Okay, because if you notice here, if this is a rectangular solid, the area, okay, it's not rectangular solid. It's a rectangle, but we're counting it being very thin this way. Does have some area here and there, but basically we're saying this is, well, I'm sorry, it doesn't have to be thin. It can be any depth. You got an area back there, but the length times width, that's the area, times the height, that's the volume. So the height is Y2 minus Y1, so that's where that comes in. And because of that, then, let me go back here and redo this a little bit, okay? And this will be rho times A times Y2 minus Y1 times G. That's equal to 0. And then if you notice, every term has that same area in it. So divide it out. Okay? And what does that leave us with now? I don't even know which direction they plan to be going. And for some reason now they flip it back around. And solve it for P2. So P2 is equal to P1 plus rho times, or rho G times Y2 minus Y1. Okay? Move those two back on the other side. It's up one thing. They're counting the, no, they're not. I guess they're counting the y's below the surface as being negatives. They haven't specially said that, but they must be. If that's a 0 and that's a y1 and y2, y1 is a more positive number than y2, so they have exchanged there. I was just going by depth, they're going by height. And it's bizarre because in my last class, which was a calculus class, we were doing this from a calculus viewpoint, and they always count depth positive going down. This is counting depth. So this will be y1 minus y2, y1 minus y2, and y1 minus y2. The reason for that is they are having positive going upward. Okay. So now we've got the same thing on both sides. Now, since y1 minus y2 is this h, then you can sort of generalize this to be the pressure at any depth is equal to some given pressure, the reference pressure, plus rho g h, because y2 minus y1 is exactly h, as you see there. So that is a roundabout way of how they got to what they did in the book. According to that last equation I just wrote down, the pressure at a depth h below the surface of a liquid open to the atmosphere is greater than the pressure, atmospheric pressure, by the amount of rho gh. Okay, now what is rho gh? Rho is the density of the fluid, the liquid. G is the acceleration due to gravity, and H is the height of that object, whatever you're dealing with. Now, if you think about this, rho density is mass per unit volume. Okay? Mass per unit volume times G is the acceleration, so that would be weight per unit volume times height, and that would be weight per unit area, which is force per unit area, is nothing like the pressure. Pressure created by that object. And Ryan is here. Good to see. Okay. So what they say here, the pressure P at any depth H below the surface of a liquid open to the atmosphere is greater than the atmospheric pressure by the amount rho GH. That's what it is. And that is often called the equation of hydrostatic equilibrium. So let's look at quick quiz 9.2. The pressure at the bottom of a glass filled with water, rho is 1,000 kilograms per meter cubed. That's a rather bizarre unit to use for a glass of water. 1,000 kilograms per meter cubed. 1,000 kilograms is a metric ton, and a cubic meter is a much bigger thing than a glass, unless you have an awfully big glass, is P. The pressure at the bottom is P. The water is poured out, and the glass is filled with ethyl alcohol, which has a density of 806 kilograms per cubic meter. The pressure at the bottom of the glass is now A, smaller than P, equal to P, larger than P, or D, indeterminate. The pressure at the bottom of the glass. If the density of ethyl alcohol is less than the density of water by 194 kilogram per cubic meter, would the pressure at the bottom be A, smaller than the pressure at the top, and not at the top, if water were in there, B, equal to the pressure when water is in there, C, larger than the pressure when water is in there, or indeterminate? You can't tell. What you think? Smaller, equal, larger, or can't tell? Any ideas? Is this one? D, you said? C? Okay. C was larger. Well, okay, now get what they're talking about. The water with the glass with ethyl alcohol in it, that's the pressure they talk about compared to P with water in it. And so ethyl alcohol is less dense. That means it's smaller mass per unit volume. So therefore, actually, it would be A, less than. But let me check. Let me first get Darius here. Okay. This is 9.2. Oops, not even in the right place. Yeah, it's A, less than. Something easier to get to. All right, there are a couple of examples here. One, oil and water. What happens when you put oil and water together? They don't mix. The oil goes to the top, the water goes to the bottom. Now, we saw with the Gulf oil spill several years ago, dramatically saw that being the case. The oil kept bubbling up to the surface. There was some oil that stayed near the bottom, but that was such high pressure, high density oil. The temperatures were so cold that it almost acted like it solidified, or it came close to that. But by and large, the oil came to the surface. Pain in the ear. Glad they said ear. That's example 9.3. If you need any of these seen, want to look at them, I'll be glad to go over them. So let me go. All right. Oh, and here was the equation we just derived. The pressure lower down is the pressure at the surface or somewhere fixed thing, plus the rho GH. Okay? Where rho is the density, G is acceleration due to gravity, and H is the depth. And rho, since rho is mass per unit volume, multiply that by depth, and you basically get an area, and a mass times acceleration due to gravity is a force, so that's a force per unit area. And P0 is called the normal atmospheric pressure, so that would be at the top. And by the way, normal atmospheric pressure, now this is not printed well. This should read 1.013 times 10 to the 5th. That's not 105. It's 10 to the 5th. That should be printed as a exponent. 10 to the 5th pascals. And as I told you before, a pascal is a tiny, tiny pressure. When Ryan just came in and opened the door, he made the pressure fluctuate by several pascals. Did any of your ears pop because of that? No. We don't even sense it. And when he closed the door, he varied it the other way by several pascals. So a pascal is a terribly small unit, so therefore it takes a whole lot of pascals to make 14.7 pounds per cubic feet. Pounds per square inch. Sorry, PSI, by the way. A pascal, on the other hand, is a Newton per square meter. Well, a square meter is a huge area, and Newton's a fairly small amount of force, so when you scatter that over a large area, you get an extremely small number, is 1 pascal. So it takes 100,000 of them to make anything worthwhile. The 14.7 pounds per square inch, a pound's bigger than a Newton, but a square inch is much, much, much smaller than a square meter. And just the differences are incredibly great. Okay, pressure does not depend on the shape of a container. And here's a fairly weird looking device. It has looks like a flask at the bottom that's being held in place here. It's sort of a rounded bottom. This light has been bothering me all day long. Thought it was better, but it's because I went down to the office and was there for just a short time. My eyes started feeling better. But it's in direct communication with this connecting device. The connecting device has another pipe and a branch of the pipe off. This has a connecting device with another pipe off of it, and this is connected by a very small tube up to a funnel, okay? And even though these two radii look about the same, that's much smaller, that's enormously bigger, but in every one of them, the height is equal. So it isn't the amount of fluid in the container, it's the height of the fluid, and that determines the pressure, and they will all be very close to the same. Now, I say that, and then I'm going to give you a little bit of a caveat here. If this was a very, very, very small capillary tube, then we get a little bit of what they call capillary motion in it, because the smaller the tube, the attractive force between the fluid and the tube, or the glass, you can't really see any here, but there usually is a little bit of film on the edge, and that smaller the capillary tube, the greater that pull is up. Now, you've got straw in your drink there, right, from Jackson's? Okay. If you had one of those very, very tiny little, almost coffee stirrer type straws, they're hard to see through because usually they're black. But if you had one that was clear, you would sometimes see that if you lined those two straws up and they were both clear, that the one that's very small might, the level looks like it goes up a little bit, but that's because of that capillary fluid. That's a completely different issue. But basically, if they're fairly large diameters with very little of that, then they're all at the same height. Pressure does not depend on the shape of the container. Do you remember, it's such an old story, I don't know if people even tell it anymore, the little boy that stuck his finger in the dam or the dike in the Netherlands to and saved the city? You never heard of that. Okay. You know, Amsterdam, or the Netherlands, much of it is below seawater, especially the coastal area, and they have the big old windmills that you're used to seeing there. They are pumping water back to sea. They're keeping it from flooding into the low-lying area there. And supposedly in the early days, this little boy was passing by and noticed a leak in one of the dams that was holding the water back, and he was concerned about it. So he put his finger in the hole and literally stopped the town from flooding. That's the story anyway. And the question is, can he hold back the whole ocean? Well, if that was near the top of the dam, or the water level on the other side was near the top, the pressure wouldn't have been very great at all. Now, if he took his finger out, that water keeps coming in, and you could flood this ultimately, but the pressure wasn't that great. Okay, just a dumb little point. So Pascal's principle is given on page 274, and here is basically the same statement of it. A change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. And a change in pressure applied to an enclosed fluid is transmitted undiminished to every point in the fluid and to the walls of the container. Okay? Now, what's the ramification of that? Number one, it says to me, fluids are very, very efficient transmitters of pressure. There's no loss. There's no friction loss. There's no line loss. There's no loss of any kind. So therefore, when you see in a garage or something those hydraulic jacks, they are so much better than one of these you have to crank by hand. You hear any of that noise there, that's produced by friction. The hydraulic jacks, they just pick it up. You know, it transmits immediately, quickly, no loss, undiminished. This principle was first recognized by Blaise Pascal. And by the way, if you haven't chosen the paper topic yet, he is one. He's a very good one. Man, he was just 39 years old. Is that right? Wow. Awfully young. That's all. And by the way, he's the one that named the unit for pressure after he acknowledged this point of fluid pressures and then worked on it. And you'll see in your text a picture of schematic of a hydraulic pump, but also a picture of a guy working under it. Okay. There is another example, 9.4, the car lift, which that was a picture of, and there's a picture of it here. The hydraulic press is an important Monique, right? Yeah. Okay. So the hydraulic press is an important application of Pascal's principle, meaning that the pressure that you exert over here, so you can exert a small force, okay, over a small area, and that's transmitted to a larger area, but the pressure is the same. So if you make the area larger, you made your force a lot larger, so you can lift a car. Did you ever think you could lift a car? You can with an appropriate hydraulic lift. Okay. I wish I could move this. It was a very poorly done slide. It says also good in hydraulic brakes, forklifts, and car lifts, and so forth. Okay, I think that's how it reads there. Small force alpha on the left produces a much larger force on the right. All right, let's see if we can find. There, as I said before, there is example 9.4, which is a car lift, and there's an applying physics problem building the pyramids. That's also, worth a read. Now, let's look at some of the pressure measuring devices. A very simple one for measuring pressure is called a manometer. Now, I don't know the root for the word M-A-N-E or M-A-N-O or whatever it happens to be. The meter part means to measure. That's what the French word, I think the Latin word, all comes from to measure. Okay, so it's measuring. I assume that's something to do with a device. Okay, one end of the U-tube is open to the atmosphere. Right here, this is open to the atmosphere. So the pressure here is 1 atmosphere of pressure. That's your P0. We had the number earlier, 1.013 times 10 to the 5th Pascal. Something like that. The other end is connected to the pressure to be measured. Okay? If P in the system is greater than the atmospheric pressure, H is positive, is less than H is negative. Okay? P in the system, the pressure in the system is greater than that in the atmosphere, then the H is positive here. Now, generally, and that's what this shows here, generally the pressure here is greater, making this H be positive. Because you see, here is the piston here, you might say, that this is pushing down, but I have pumped up and gotten water up to here, so this is your rise in that. That's the MGH that we talked about before. That's the H, your change of H. And if the pressure over here, P, in the system is greater than atmospheric pressure, the H will be positive. Otherwise, if it's negative, it will be less. All right, now, most of these formulas that you have seen and probably will be seeing, unless it's pretty obvious, not, the pressure P is called the absolute pressure. Okay? Now remember this, your pressure at any value is your atmospheric pressure plus mg rho g times the height. Okay? Now, if you subtract P0 from both sides, then the difference in this is rho gh, and that's called the gauge pressure. If this is the reference pressure, I guess you would say, could be atmospheric pressure, whatever you're using that. Earlier we're using atmospheric pressure. Whatever your reference pressure is, then the difference between that is rho gh. Sometimes your device is measuring this, not measuring the total pressure on it, but the difference in the pressure and the atmospheric pressure. Okay? Any of you ever checked your car tire pressure? You have somebody else do it, huh? Okay. If you were to get, and they call those, goodness gracious, I just had the word on the tip of my tongue and now it flew off. Those devices you stick on there, okay? They are giving you gauge pressure because that pressure is the difference between that and atmospheric pressure. Otherwise, when you're holding it in the air, it would read 14.7. It doesn't. It reads the difference of 14.7 and whatever your tire is holding. Okay, that's the gauge pressure. And a lot of times, that's what we're studying or working with. Now, another pressure measuring device is a barometer. Okay. In fact, I bet you've heard most weather people, either on radio or television, say the barometric pressure is holding steady at 30.0, blah, blah, blah. Okay? What they mean by that is what is the, let's see, how is that? You're measuring that. Generally, that's measured against a vacuum. It's not always, but generally it is. So it's absolute pressure. Okay. This was invented by, pretty sure he was Italian by that name, Torricelli, and he lived from 1608 to 1647. So it was back along about the time when France was blossoming and leading most of the science and the arts in many ways. The Italians were in on it as well. Okay, and here's how a barometer works. A long closed tube is filled with mercury. Okay. A long closed tube filled with mercury, inverted in a dish of mercury. What I really want to do is, and this is sort of a big takeoff here, but I wanted to give this example first. It has something to do with pressure, but the first semi-useful, somewhat accurate thermometer I think ever invented was by Galileo. Now, you think back, they didn't have any kind of thermometers, did they? Things felt warm, cold, hot, cold, cool, whatever. That's about all they could do. What Galileo did, he came up with a a beaker of water. And it's one of these beakers with the long, thin necks on it. Okay, big bulb at the bottom, long, thin neck, and then spout. And he had a pan of water here. And what he did, he took the beaker of water and flipped it over. Now, the beaker of water wasn't full, okay? The beaker of water only came to so far down the neck, okay? But then he flipped it over in the pan of water, okay? And as the water heated up that was in the beaker, he didn't pour it out into the pan, he flipped it over with the bottom down into the water of the pan, okay? And then he had the big bulbous beaker up top, and here was that thin neck. And he measured the level of the water in the neck depending on what the temperature of the water was up here in the bowl, you might say. And as the water heated up here, it pushed the level down. Let me say that again. He flipped it over, and all of it emptied out of here. So that was air left here. You had water up to here in the, they show it here. I'm going to move it down here. Up to here, and then the rest was in the pan. Okay? Now, if the air inside the beaker, the bubble of the beaker heated up, the air expanded and it pushed the water down and into the pan, and then the water in the pan moved up some. Okay? And that was how he measured temperature, and he made up a scale and put it on there. The problem with that thermometer, there were probably several, but the major problem with it was atmospheric pressure on the water, which he didn't even know existed. As atmospheric pressure changed, it would push down here, forcing the water back up in the thing and compressing the air. And if the atmospheric pressure dropped out here, then it would suck, the water would come down, and you would have a change in this thermometer temperature when it really was a change of pressure. So that was a problem. Isaac Newton came along and solved the problem, as he did with many of the things with Galileo. He expanded or solved. And what he did, he took it and had something very much like this, and had the tube more like this, a long, thin capillary tube, absolutely filled with water or liquid, mercury, alcohol, something. And then when he flipped it over and got the base down here underneath the surface, basically what he had was a vacuum up here with almost no air or molecules in it. Now, you probably had some. But then what you had, the temperature of the water here would force that up or down. And because there was nothing here, it was a vacuum pretty much there, just empty space, then there was no resistance to the movement. So this wasn't affected by atmosphere. And in fact, he actually took that and sealed it off. And sealed it up so the atmospheric pressure couldn't have anything at all. And when this liquid heated up here, it would force its way up the tube, and when it cooled, it would come down. That was a much better thermometer, and that's what we still use as thermometers. How many things of Newton's do we still use? No one's ever improved on it. Okay? But backing up here, what he had was a combination of a barometer and Galileo had, a barometer and a thermometer, and Torricelli, many years later, like centuries later, he came up with the idea that we could use that type of device to measure pressure. Okay? And he had the closed tube filled with mercury, inverted in a dish of mercury, and therefore what separated out here was basically a vacuum. The pressure in here was zero. There was no pressure there. Okay? But the atmospheric pressure was here, and it forced this up here. Now, with no pressure here, it sucked up the mercury from here and tried to hold it to a level. The greater you increase the pressure here, the more it rose here, the more of this pressure dissipated, then this would drop so far. And that was your early thermometer. why mercury rather than water or alcohol or something else like that? Mercury is very dense, a liquid but very, very dense. So therefore, a small, okay. 1 atmosphere of water, 1 atmosphere of pressure is about equal to 10 meters of water. That would be more than a 3-story building, okay? So if you had a manometer or a barometer that had water in it, you're going to have a column about 10 meters tall to measure 1 atmosphere of mercury, 1 atmosphere of pressure. Whereas the mercury thermometer or barometer has mercury is 13.6 grams per cubic centimeter. This density is way, way more than that of water. So therefore, you can have a much smaller tube to measure normal pressures. Okay. So this measures atmospheric pressure as rho GH. Rho being the density of mercury, a large number, G the acceleration due to gravity, and H is the difference between the level in the hat up there, the top of the test tube or whatever this is. That distance here between this water level and that water level, that is basically your delta H that you're worrying about. That measures your atmospheric pressure. Okay. Now, one of the big problems with pressure is you got so many stinking units that people use to measure. We've already mentioned pascals. We've mentioned PSI, pounds per square inch. Some people use just the 1 barometric pressure as being 1 bar barometric pressure. So you have so many bars. And others choose small devices, devices that are going to have a great deal of precision in your measurement. Others can be pretty gross. Okay? So 1 atmosphere of pressure is defined to be the pressure equivalent to a column of mercury that's exactly 76.0 centimeters of mercury. So here are the various ones. 1 atmosphere of pressure, that's one way to measure how many atmospheres of pressure. Outside today is approximately 1 atmosphere of pressure. That is about 76 centimeters of mercury in a barometer. Okay? That would be, and we've already given this one, 1.013 times 10 to the 5th. That's 113,000. Lose your 10 to the 5th pascals. That's a very okay. And then we mentioned again 14.7 pounds per square inch. And this has all of them either. You have torrs, you have goodness, I can't think of all the others now. Atmospheres, centimeters of mercury, of course that could be millimeters of mercury, it could be inches of mercury. It's measuring the same thing, but different units for height. Okay? Then you have pascals, or that could be kilopascals, or it could be megapascals, or to use the basic unit, that would be there's another equivalent I can't think of right now, or 14.7 pounds per square inch. Now, you might not think the atmosphere is putting much pressure on us, do you? I talked about this before, didn't I? 14.7 pounds, that would be this book, I'm guessing, weighs 3 to 4 pounds, approximately. Okay? To get to 14.7 pounds, you need maybe 5 of these books. Do any of you want to carry 5 of these books around? Okay? Pretty heavy stuff. Okay? Let me get Embry here before I forget that she came in. I've got to find her first. There you are. All right. So that's quite a bit of weight, 14.7 pounds. Okay? Now, that much weight is being on, and this is about a square inch. Your 2 thumb joints together. That's about an inch this way and an inch that way. So if you picture these, how many square inches your body has, that's a lot of square inches. A whole lot of square inches. Multiply that by 15 pounds per square inch. We have an enormous amount of pressure on us, of force on us. 14.7 pounds per square inch. But multiplying by our body square inch size, you'll see enormous volume, a massive quantity of mercury weight on us by the atmosphere. So you might ask yourself, why are we not crushed? Any good answer for that? What's that? Yeah, gravity would also tend to make us crushed, but gravity is what's pulling the air above the earth down. That's what you're measuring there. That's how much air there is above you, how many pounds of air. So it goes up quite a ways to get that many pounds of air. Well, the reason is that our bodies are pushing out. We are pressurized bodies. Okay? That's why when you cut your arm, you just don't have air sucking into the wound. Blood actually comes out, which is a very good thing. You don't want the air going in. You want blood coming out to prevent infection from coming into your body. So it's actually a very good thing we're under pressure. More than 14.7, I guess around 15 pounds per square inch. So that's why, no, it doesn't really, we don't sense, we don't feel that 14.7. This is an absolute pressure. Our gauge pressure would be 0.3 pounds per square inch. The difference in that in atmosphere. Okay. Usually when I go over that and tell how much we are pressurized, I then give the example of astronauts. And especially that team of astronauts that went up. I don't know if y'all recall, we didn't really get a very successful space station out there. The Soviets decided to do that before we did, and they got one up there. It was called Soyuz, I think, or something like that. And for a while, that's all she wrote. That was all that was out there. And at some point, we started cooperating a little bit better. And so we would send people out there to be on Soyuz. I think that was what it's called, Space Telescope. Okay. It seems like either we put one up or the Europeans did and we helped, because they didn't have the launch vehicles as we did. And they got one out there, and it just didn't do too well, and ultimately fell out of orbit and crashed, burned up in the atmosphere pretty much. Probably parts of it fell into the ocean. We never saw it or detected it, but it was pretty trashed. So after a while, we were back using the Soviet space station with them to do any of our research. and they had what they called unmanned space vessels to come up and resupply. They had people in the space station, but Darius is here. And I guess I didn't realize that we lost Darius. I don't know if we permanently did, but he was here. Okay. So they had these unmanned, sort of computer-driven, vessels that came up to bring supplies and haul stuff back and that kind of stuff. I don't know if they did too much coming back. But one of their, I don't think their technology was quite as sophisticated as ours. One time, one of those cargo ships, they called them, came in too fast, too furious, not quite where it's supposed to be, and just ripped the mud out of the station. So badly affecting, there were leaks, and the Soviet cosmonauts that were inside had to retreat to an interior space because the outer part was damaged. So this was like 2, 3, 5 guys or something like that, all living in an incredibly cramped space. They couldn't do much of what they had been doing because the outer part had lost a lot of its pressure and things and was exposed to the outer space. Well, the U.S. had the most experience in spacewalks and we had vessels we could deliver people fairly easily. This is back with the shuttle fleet. So we sent up teams of repair astronauts to help the Soviets repair their station so those poor guys could get out of that really cramped little space, miserably cramped little space, which they've been for weeks, if not months, okay? So we went up there and were helping. Well, when that cargo ship hit that, it mangled metal. I mean, it broke things, it bent things, jagged pieces of metal were out there. Well, here the astronauts had to go up there, and the cosmonauts too, and tethered, around in their spacesuits. And those are big, really bulky, awkward things. Why are they so big and bulky and awkward? Well, number one, they have to be made out of aluminized or some type of material like that, maybe even silver, that reflects most of that dangerous, harmful, deadly radiation that's out there in space. See, we have that huge atmosphere over us that produces 14.7 pounds per square inch. That's a lot of air, a huge column of air that's above us, making that much pressure on us. And that atmosphere, our beautiful, wonderful atmosphere, deflects most of that harmful radiation. In fact, there is a whole layer of our atmosphere called the ionosphere. That harmful radiation hits that, and rather than penetrating, it knocks off electrons and it forms ions. And that ionosphere then keeps more of it from coming through. So it's a really incredibly fantastic system that is there. Well, they first have to be silvered outside so they don't get exposed to that radiation. But the other thing is they have to be pressurized. Because remember, we're pressurized to about 15 pounds or more per square inch. And in outer space, there is no pressure. There is no atmosphere above you. So the spacesuits have to have air pumped into them to keep that pressure. Okay? Now just imagine then, if they were working on trying to repair, and you don't see well because you've got this big visor, and it has to have all sorts of super duper sunglasses, built into it to keep that radiation from hitting their faces and their eyes. They'd be dead. They'd be blind in no time if that harmful radiation hit them. So it's hard to see. You don't have much peripheral vision, and you're in these big bulky spacesuits, and you're tethered and stuff, so you don't float off somewhere. Well, what if they were working on something and didn't realize they were coming up on a jagged piece of metal, and that metal ripped the spacesuit. All that pressurized air out into outer space where it's almost zero pressure. Then, all the pressurized gases and fluids in our bodies out our orifices, our eyes, ears, mouths, stuff. There goes our blood, our oxygen, everything dead in an instant. No time for the radiation to kill them. They literally are pressure bombs, okay? And they disappear. Not the greatest, maybe, thing, but realize there could not have been a more hazardous job, I don't think, on this planet than what they were doing repairing that space station. All right. Let's look before, there is a quick quiz, 9.3. And by the way, I mentioned just a few minutes ago, one measure for pressure is very close to an atmosphere, and it's called the torr. Guess who it was named after? Torricelli. Okay? They named that unit after him, but it's not an SI unit, so it's hardly ever used anymore. Okay? Now, before we get to blood pressure, quick quiz 9.3. Several common barometers are built using a variety of fluids. For which fluid will the column of fluid in the barometer be the highest? And now it says refer back to table 9.1, which was quite a few pages ago. It was last week we did it. It's on page 269. Okay? Now we're looking for fluids. So forget about ice, aluminum, iron, copper, silver, blah, blah, all that first column. There, we finally have it. We have water, glycerin, ethyl alcohol, benzene, mercury, and let's just do those. Okay? For which fluid will the column of fluid in the barometer be the highest? A is mercury, B is water, C is ethyl alcohol, D is benzene. Which of those? And you find just ignore glycerin, find those as the 4 of the top 5 in the second column on page 296. Which you reckon would have the highest column? Give me some help. Any of you turn back to the table and look at them? See in the table the densities, so which ones would need to have the highest column? The more dense or the less dense material? The less dense, okay? And which of those 4 is the least density? Ethyl alcohol, very good. The shortest column would, of course, be the mercury. It's way denser than any of the other. So that should be C. 9.3 should be C. Good for them. They got it right. Okay. Now let's consider blood pressure. Any of you ever taken blood pressures? Okay, you have. Most of you have had them taken, I bet. I know I have every time I go to the doctor. Pretty much, they do. Blood pressure is measured with a special type of manometer called a sphygmomanometer. Okay? I think that's how you say that. The pressure is measured in millimeters of mercury. Not centimeters, but millimeters. So back here, if it's 76.0 centimeters of mercury, how many millimeters of mercury would that be? I see mouth moving, but I can't hear. 760 millimeters, because millimeters is a smaller unit, so you make this bigger by 1 decimal. Move that decimal over. So 760 millimeters of mercury is considered 1 atmosphere of pressure. And that's what the blood pressure is measured in. It's called a sphygmomanometer. Okay? So what you do, in the old days, they don't do this much anymore, they pump up using this bulb to increase the pressure on your arm. And they're listening here to see when they no longer hear a pulse. When that is contracted enough, the cuff is contracted enough that it stopped the blood from flowing. Okay, that's going to be the upper number. That's the diastolic. Systolic on top. Okay. And then they release it, and then the air slowly goes out. This is a valve here, and you watch the sphygmomanometer, the pressure come down, while at the same time listening. Well, shortly after it does, you start hearing it come back, but what you're listening for is when it gets back to normal. Okay? And when it gets to normal, that's the diastolic, right? Okay. Now, what you want those numbers to be? Second? 128 over 80, is that what you said? Okay, that's pretty much considered normal. Is that here in the book too? I saw you point. No, you're just pointing. That's pretty close to normal. Okay. I've been very lucky. I typically have a fairly low blood pressure. I was at the doctor yesterday, and it was 136 over 76 or something like that, which isn't bad. You know, it's a little high on the systolic, but the diastolic is always quite good. But most of the time when I have it taken, I'm around 117. So I'm lucky that way. I think all three of my siblings take blood pressure medicine. I don't have to take any. So, okay. But anyway, that's what you're measuring. Okay. And that's basically what you do. Before we hit Archimedes, let's do quick quiz 9.4. Blood pressure is normally measured with the cuff of the sphygmomanometer around the arm. Suppose the blood pressure is measured with a cuff around the calf of the leg of a standing person. Would the reading of the blood pressure be the same here as it is for the arm, greater than it is for the arm, or less than it is for the arm? What do you think? Greater, you said? Yeah. Yeah, and let's deal with the systolic, the bigger number. I think because it's further from the heart, this is just a guess, that would cut it off sooner. So I think it is less, but let's see what they say. Okay? This is 9.4. Actually, it says greater than it is for the arm. And that was my first, I think they may be talking about the diastolic, because there I think you would come back to normal faster because you have, usually when they take it, they have your arm up and relax and that kind of stuff. So you're right about the same height as the heart. Okay? So you, yes. And when you're standing up, now the pressure is greater down here than it is up here.
Most people will have blood pooling or fluid pooling in their feet.
Say that again?
You will have blood pooling or
Right.
fluid pooling in your feet because of gravity.
Right.
So therefore your distal pedal pulses or your blood pressure are often non-existent. So it takes a longer time for you to heal up here. So
Right. And that's probably also the reason that sometimes older people have more swelling in their feet, because
you also have the circulation issues.
circulation issues. Yeah. They, if you think about it, your veins especially, probably the arteries too, but veins especially, have these little flapper valves in them. And so therefore when you're pumping the blood up in between beats, it flows back down so the blood doesn't, and other fluids, the they leak, you know, and that kind of stuff. So people, I know my mom had pretty bad swelling in her legs as she got older, and her closest sister was worse than her. She really had some problems with that. But my mom could kind of control hers with diuretics and things like this, but then that would lead to problems in potassium balances and stuff like that. So anytime you start messing around with the body, you have to be very careful, because one thing you do to help this might hurt something else. And I think we're still learning that. On page 277, there's Applying Physics 9.3 talking about ballpoint pens. Now, what difference does this make? This is Courtney Humes is here. I'll get you in the right line here. All the way across the page, so it's hard to keep up. Okay? Ballpoint pens, believe it or not, depend on pressure too. You have to have enough pressure to get the ink to come out. Okay? And so it's well worth a read. But I will tell you this. Another dumb story, but it's not so dumb, it's sort of funny. You know, we were in the space race with the Soviets, right? The Soviets, the Soviet Union. That was Russia and Ukraine and Belarus and Georgia and Kyrgyzstan, Kazakhstan, you know, all those unions. That was the Soviet Union, okay? They, together, had a really powerful system. Wasn't sustainable, but a powerful system. They got ahead of us in the space race and some of the other things. Yeah. So they were ahead of us, and we were competing like crazy. And one of the earliest flights, manned flights, we found out, and they found out too, that when you got up into outer space, ballpoint pens did not work well anymore. Well, we had NASA. NASA was, because we were trying to catch up with the Russians, they had almost unlimited budget. And they put out proposals to come up with a pen that would write in zero gravity, okay, at very low pressures. And different groups got together and, or, you know, started working on the stuff, and they probably spent thousands, hundreds of thousands of dollars on developing pens that would write in outer space. Well, the Soviet Union, though they got ahead of us, they were ahead of us, they didn't have the resources we did, or NASA did. And it just happened to be, remember the Soviet Union split after Gorbachev, he enabled it too, and then it went back to being Russia and Uzbekistan and Kazakhstan, and all these were independent countries again. Well, I just called the name of it. Ukraine was probably the next biggest and most educated, best educated, and you know, strongest, but it was weak when it pulled away. Well, the Russians had done something else. They were the big guys, right? So when they would absorb these other states, republics, when they were still Soviet Union, they made a special effort to get Russians to move to those other areas, so Russia would still be the big dog, you know, and they wouldn't have ethnic conflicts because there were Russians there and they didn't want to complain against the big dogs back home. So, and that's gotten them in trouble in what's that republic that's mostly Islamic, that they keep having all the terrorist activities. It hasn't been much lately, but it was for a while. It seems like it starts with a C, but I can't think what it is now. The what? Not Czech. I can't think. It may not be C, but they, you know, periodically they'll do some sort of terrorist activity against the Russians. They're in a mountainous area, they can hide, you know. I can't think of it, you know. But anyway, And some of them were in the space program, the Soviet space agencies. They all participated. Well, when they split apart, they sent all those people home. Well, Russia was still big enough to keep having the space program. But even Ukraine, the next biggest one, nowhere close. They could not, they didn't have enough population, enough revenue, or enough anything to maintain a space program. Well, some of the Russians that had been sent to live in Ukraine, native ethnic Russians, when they split, they wouldn't let them come back. And one of those was a guy named Dr. Leo Bolshinsky. There were many, I'm sure. But he had worked all his life in the Soviet Space Agency. And here he was in Ukraine that didn't have a space agency. They wouldn't let him move back to Russia. So he had limited possibilities of what he could do. Now, he was a brilliant guy, a PhD, physics, really sharp. But the universities in Ukraine only could hire so many people, so he was having trouble getting a job. So he and his family immigrated to the U.S. And he sort of had trouble getting a job here too, but he came to work here. Back then we were at Western State Technical College, and maybe early in the process after we merged, he was working here. He was fantastic. He worked so hard, do so many things. Anything I needed him to do, he would do. He really built our program. He really improved it. And one time we were talking, he told me this story. When the Soviets found out that pens wouldn't work, NASA, on the one hand, set out a request for proposals and paid people thousands, tens of thousands, hundreds of thousands of dollars to develop pens that would work in zero gravity. Dr. Bolshinsky said, we just started using pencils. And I went, duh. They didn't have the money to do that. So they just went, pencils still work in outer space, pens don't. So that little blurb there will feed into that pretty nicely. All right, let's move on to the next one. This is 9.6 on the old slide, but it's 9.5 in our book. And this is Archimedes' principle. And here is, I don't know how accurate a picture that is. Remember, Archimedes lived 200 to 300 years BC, okay? Way back then, okay? Way back then. And he was a Greek mathematician, physicist, engineer. He had to have been probably the brightest person within a millennia of the time he lived. I can't imagine anyone brighter on the planet. There could have been maybe a few Chinese or somebody out there. He was absolutely incredibly farsighted. Yeah. So he did many things. What we call Archimedes' principle, what we're going to be talking about, is a buoyant force. He was an inventor. Do any of you know what an auger is? I grew up on a farm in Georgia, and we came in with a truckload of grain or a trailer load of grain or something like that, and needed to get it into the grain bin. We had this auger, this device that was a metal sleeve, and it had a screw in it, and a motor at the top, or a motor somewhere along the way, that turned the screw, and that lifted the grain out of the truck. Okay? You know what that was? That Archimedes screw. He invented this thing 300 years ago, and it's still no one's beat it yet. Okay? He invented that. He was living in a very small city-state in Greece, and lots of people wanted to invade that. He came up with ways of taking mirrors and lenses up on the mountain, and when the wooden ships were coming in to invade, adjusting those so that they beamed down on the ship and set them on fire. He came up with all sorts of devices. I'm not sure if he didn't invent the catapult. he invented things that no one had even thought of before. And he came up with all sorts of brilliant ideas. Mathematician, physicist, engineer, he did it all. Great paper topic if anyone wants to write on him. So let's move on from there. And anything you find in the book, of course, could give you an idea, but you got to find an outside source. Here is Archimedes' principle. Any object completely or partially submerged in a fluid is buoyed up by a force whose magnitude is equal to the weight of the fluid displaced by the object. Okay? Have you ever played in the swimming pool? Everybody has, right? I can remember as I was sort of senior teenager and young adult, especially when there were a bunch of kids in there, it was, I became the one to throw them up in the air, you know. They just loved that splashing and stuff like that. And they were real easy to lift underwater. Get my hand under there, have them step in my hand, and pick them up and throw them into the air. They go flying into the air. They were real easy to lift when they were mostly underwater, but when they got in the air, they were a lot heavier because of the buoyant force. They were displacing water, and that reduced their weight. They're buoyed up by a force equal to the weight of the water displaced by that object. When I was in the Navy, I was on an aircraft carrier, okay, USS Forrestal. I told that to somebody who was in the Navy too. He said, "Oh, the forest fire." They had a couple of really major fires on them over their history, not while I was on board, but they were known as the forest fire because they had major fires. But anyway, this aircraft carrier, just the flight deck that the planes took off and landed on, was about 6 to 8 inches thick of solid steel. The flight deck, just that flight deck. The rest of the ship was really heavy, all made out of steel. And that aircraft carrier had lots of equipment on board, lots of heavy equipment that could pull and push and planes around, pick up ammunition to load, stuff. A lot of heavy equipment. Generally, the aircraft carriers carried on max between 5,000 to 6,000 people, and all the food, water, fuel, ammunition, oil, and about 90 aircraft on board with all their fuel equipment and all their people that take care of them and stuff and all their tools. It was incredible. They had big boilers on board and stuff. I don't know how much that aircraft carrier weighed. Hundreds, if not thousands of tons. And yet it floated. Why did it float? It displaced as much water as its total weight was. So it displaced a lot of water. Because inside that was empty space, as in holds that were not full of things, So on average, it had to displace as much water as its total weight was. And it sat up off the water, out of the water, a good high distance. So therefore, it had to be way deep in the water, and it literally was. It was about 11 stories above the main deck and 11 or 12 or 13 stories below. So you had stories of spaces below the water line. You had to have, otherwise it wouldn't have floated. Okay? Archimedes' principle. Now I was also on a submarine for one summer, and submarines go back and forth. When they want to be on the surface, they pump out this one thing with compressed air, forcing the water out, and then when they want to dive, they have to let the water come back in there. So they have to always have enough compressed air pump that water out, or else they're not coming up again. And that has happened to a couple of subs early on in the development of submarines, but even fairly recently there was a Soviet submarine that, it's hard to say they sank. It was below water and never came up. And they had lots of investigators somewhere up in the North Sea or somewhere there. So it does happen. We've lost a few ourselves, but pretty bad. Here's how we describe and talk about buoyant force. Okay? The net upward force is the buoyant force. Okay? You see at the top of this, they just showed a ball here. Top of the ball, the force is downward because it doesn't have as much water above it. Remember, water pressure varies with depth. Down here, the force is greater because there's more water above it, so that the pressure is greater. So therefore, the difference between the upward force here and the downward force there, that's the buoyant force, pushing it upwards. Okay? The magnitude of the buoyant force, and this is a cannonball, a very heavy object, okay? The magnitude of the buoyant force on a cannonball equals that of a, this could be just a metal ball, a wooden ball, or something like this. Something heavier than water, but not as heavy as a cannonball. Well, the difference here is that, well, I don't see much difference here, but the thing is, it would sink faster because its weight is greater than the difference with it. As it's got the same volume, it's got the same buoyant force. It's displacing the same amount of water. But if it's heavier than this one is, then the difference is going to make it fall faster. So the upward force is called the buoyant force. The physical cause of the buoyant force is the pressure difference between the top and the bottom of the object. It's just really that simple. The pressure difference between the top and the bottom of the object. And whether it's a lightweight ball that's just a little heavier than water, or a cannonball that's really heavier than water, the buoyant force is the same if those are the same size. It's just that this weight is greater than this one, so it will fall faster. But not as fast as it would in air. Okay. The magnitude of the buoyant force always equals the weight of the displaced fluid. So if you had two balls of exactly the same size, they're going to have the same buoyant force. Doesn't matter what their relative weights are, they will have the same buoyant force. And that buoyant force will be the density of the fluid. Remember, rho, that's not a P, that's a rho of the fluid, times the volume of the fluid displaced, times the acceleration due to gravity. This is mass density. Mass per unit volume times volume, they can't follow. Mass times acceleration due to gravity is weight of the fluid, the weight of the fluid being displaced. The buoyant force is the same for a totally submerged object of any size, shape, or density. Okay? I don't like that statement. The buoyant force is the same for a totally submerged object of any size, shape, or density. There's something wrong with that statement, the way it's portrayed. I think what they're trying to say, the buoyant force is the same for a totally submerged object of the same volume, no matter what its size, shape, or density is. If it has a certain volume, then it's going to have the same buoyant force no matter what, whether it seems like that size, that would be referred to right. No matter what its shape is, no matter what the density of the stuff is, if it's not the same size, it's going to have the same buoyant force. Okay? No matter what I think they just got a word or something out of order there. Okay? I don't see that in the book anywhere, so I can't refer to it. The buoyant force is exerted by the fluid on the object. Whether an object sinks or floats depends on the relationship between the buoyant force and the weight. If the weight of the object, when it's fully, the weight of the object in the air, and you put it in the fluid, and you make it go down into the fluid. So in other words, it's got displacing a certain amount of water. The buoyant force, if that buoyant force is greater than the weight that it had before, it's going to bob back up and float. And it will only displace its weight of water. So if only a third of it gets below the water line, that means that volume of water equals the weight of the object. If it's denser than air, then the whole thing falls and it displaces the entire body. Okay? So whether it sinks or floats depends on the relationship between the buoyant force that's being exerted on it and its weight. If its weight is greater than the buoyant force, it's going to sink. If the weight is less than the buoyant force, maximum buoyant force, it'll float until they're equal. Now, this was something I found hard to believe. I've always been sort of heavy, as far as verging on obese, and but I was never a swimmer. My parents didn't swim, so they didn't take us swimming. So I was a non-swimmer. But I had to take swimming when I was an undergraduate at Georgia Tech. Every male then, not the females necessarily, but every male had to take it. It wasn't really a swimming course, it was a water survival course. And in the water survival course, a 10-week term, we had PE twice a day, so you had 28 sessions, 10 weeks. The first, every 2 weeks, you would have a big major test that you had to do, something you had to complete. So you practiced for 3 times, and then you did it the 4th time. Okay, then you practiced for 3 and did it. The first test was a hands-tied test. You tied your hands behind your back. No, I'm sorry, the first test was the feet-tied test. They tied your feet together, but then they also tied the strap around your waist so that the angle that your legs were less than 90 degrees. And they lifted you and put you into the pool. And you had to stay there for 45 minutes, and you did tricks and various things while you were there to earn extra points. Well, we had 3 times in the pool, approximately 1 hour periods to practice for this. I was a total non-swimmer. There were like 2 or 3 of us in the class that were non-swimmers. They had us go down to the shallow end of the pool and practice our breathing techniques and all this kind of stuff, because basically what you do, get as much air in as you can and then keep as much underwater as possible. And then when you needed to breathe, you came up, blew out the air you had, sucked in more, and then went back underwater. And if you do that, you can stay out there, hang around for hours, and you'll starve to death before you drown. Okay, if you do that, and you can just keep doing it. I didn't want to. So anyway, I practiced the breathing techniques in the shallow end because I wasn't a swimmer. And then they tied my feet and put me in the water. So when it was time to get the air, I could feel a little bit of air up here. So I came up and I was going down. Okay, I got as much air as I could, and then pushed to come back up. I brought the surface again, and then went to get more air. I was going down again, and I didn't realize it. I was a sinker. The coach could not believe it. Most sinkers are muscular and low body fat, really dense, structures. Even people who were really well shaped and everything else, they still most of them floated. It was only rarely you got into the sun. I didn't look at it like that at all, and yet I was sinking. So he was going to convince me I was not a sinker. So he had everybody beginning of the next day of class, hold just to the edge of the pool and get as much in the water as you could, with only your mouth above the water. He said, now suck in all the air that you can take, more and more and more. And he said, when you finally get all you can, then slowly, just don't make any sudden moves, slowly no longer hold on to the edge of the pool. And the people who were watching it said everybody bobbed up, and I felt like I was in the bottom of the bathtub. I saw the swirling as I just went to the bottom of the pool. I said, Fowler, you're not doing it. So he had me go, And he stood right over me and said, "Suck in there." Suck. I just, as much as I could, so I can't believe it. So that class on, he had me wear floaties. Now this was a freshman in college having to wear floaties, because I was a sinker and I could not possibly pass the course, not having good strokes. I was not familiar. I didn't. So sure enough, I didn't. So couldn't believe it. And even to this day, I barely float. I put on some more volume, but I've got really dense bones is the only thing I can figure out. They actually did a bone density test. They said, "Wow, okay." Not in the swimming class, but later I had that. So Archimedes' principle on a totally submerged object, the upward buoyant force, B, which is the density of the fluid times the volume of the object times the acceleration due to gravity, that is going to be B. The downward gravitational force is the weight of the object. That's the density of the object times the volume of the object, same volume, times G. So these two terms are exactly the same. It's just the difference in densities here. If the density of the fluid is less than the density of the object, it sinks. If the density of the fluid is greater than greater than the density of the object, then the object is going to bob to the surface, which I never did back then. All right, how are we doing? Oh, you just made it in. All right. So that's Raven and Bria, right? Yeah. Got to get you on the right line here. The bottom part of the alphabet just didn't show up today. You're the only one of the last 7, I think, that showed up. I don't know where the bottom part of the alphabet is today. So therefore, if the buoyancy is that and the weight is this, if the object totally submerged, then the net force is the difference between the buoyant force and the weight. If the buoyant force is greater, it's going to bob up and float. If the weight is greater, then it will sink. Okay? Displacing exactly its weight of water. And so it all depends on the difference of the density of the fluid to the density of the object. And frankly, people are supposed to float because you got your lungs that have quite a bit of air in them, and fat tissue is supposed to be less dense than and you're mostly water, so that's the same density. It's basically only the bones and muscles, and even the muscles are pretty close to the same density, or a little on that. But I must have had really dense bones is the only thing I can figure, because most people float pretty easily. Now, if you go out to the ocean, because salt water has higher density than fresh water, because you have salt dissolved in it. So most people really float in that. And they say at the Great Salt Lake in Utah, you float even easier because it's a higher concentration of salt. And they say that in the Dead Sea, over there in Israel, Jordan, or whatever, it borders the Dead Sea, that is really, really dense with salt. And they say you can't possibly sink, okay? You bob up like crazy because the density of the fluid is a great deal higher than the density of most bodies. Okay. Now, totally submerged object, the object is less dense. If the object is less dense than the fluid, and you force it down there, it's not going to go there on its own. You force it down there somehow. So you have a string on it that you're pulling, I don't know how you're pushing down on something. You're forcing it down there. The buoyant force is greater than the weight, and therefore it's going to bob to the surface. Okay? The acceleration will be upward. That's if the density of the object is less than the density of the fluid. Most woods are less dense than most fluids. Okay? Not mercury, but other fluids. But a totally submerged object, if the object is more dense than the fluid, the the weight is greater and going down, the acceleration will be down. The object accelerates downward, but at a slower speed than it would be, slower acceleration than it would be if it was in air. Because air is a fluid, it just has a very, very, very low density. Okay? Now, so let's look at the floating object. The object is in static equilibrium. The upward buoyant force is balanced by the downward force of gravity, so the volume of the fluid displaced corresponds to the volume of the object beneath the fluid level. The volume of the fluid displaced corresponds to the volume of the object. Have they said that wrong? Okay, no, of course that's right. The volume of the fluid displaced corresponds to the volume of the object beneath the fluid surface. Yeah, those volumes are the same because the object went down, forcing the fluid out of the way. And it does that until it reaches the same weight of fluid as its own weight was, and then the rest of it floats. Okay? So Archimedes' principle for floating objects, the forces balance. So the density of the object and density of fluid is equal to the volume of the fluid ratio to the volume of the object. I do not like to write that as a ratio. What I would do, rho of the object times volume of the object is equal to rho of the fluid times volume of the fluid. Okay? Now, one thing this does ignore is buoyant force of air. That is so incredibly small that most of the time we can't ignore it. If you go back to that table 9.1, on page 269, if you notice air, its density is 1.29. That's kilograms per cubic meter. If you look at water, that's 1,000 kilograms per cubic meter. What is 1.29 compared to 1,000? That's less than 0.1%. I mean, way less than 0.1%. Yeah, you can ignore air. Okay. So, they write it like this. I like to write it the other way. Rho of the object times velocity, volume of the object is equal to rho of the fluid times volume of the fluid. Okay? It neglects to, okay. The two forces are equal in magnitude, opposite in direction. The force due to gravity downward is equal to the force due to buoyancy upward. And if you did these, multiply those two together, that gives you the mass, because this is mass per unit volume times volume. Mass per unit volume times volume. So you get mass of the object equal mass of the fluid times G, which is the same for the object and the fluid. So yeah, everything balances. That's why it's equal. Okay? Now, all right. There's a couple things here I don't see them covering in the slideshow. But before you leave buoyancy, let's look at quick quiz 9.5 and 9.6. Atmospheric pressure varies from day to day. Obviously, right? The level of a floating ship on a high pressure day is higher, A, lower, B, or no different than on a low pressure day. So atmospheric pressure varies from day to day. The level of a floating ship on a high pressure day is higher, lower, or no difference from a low pressure day. Want to make a guess? That's A, B, or C. A is higher, B is lower, C is no difference. Second? No, C, no difference. I tend to agree with you if it was said not much difference or negligible difference. I would say that's absolutely correct, okay? Because most of the time we ignore the buoyant force of air. But if you really did very careful measurements, then there may be just a slight difference. Let's see which they're talking about. This is 9.5. Yeah, they say none. Okay, I agree with you. It's so negligible, I don't think you would ever even be able to measure it. Okay, 9.6. The density of lead is greater than that of iron. You can look it up in the table. And both metals are denser than water. Is the buoyant force on a solid lead object greater than, equal to, or less than the buoyant force acting on a solid iron object of exactly the same dimensions? Say again. A was greater than, B is equal to, and C is less than. Equal to. You're absolutely right, because they're both totally submerged. The buoyant force is the mass of the, and if they're the same volume, they displace the same amount. So that, sure enough, is 9.6 is B, equal to. 9.5, example 9.5 is the red tag special, strange title, red tag special on crowns. This was actually the story that has gone down through history about Archimedes. And one of the ways he came up with this principle of his king, whatever the small city-state was it Sicily or Syracuse? Syracuse, it seems like. Whatever it was, the king of the city that he lived in had been given this really ornate, beautiful crown by this rival king he didn't trust. And he didn't know if the guy was buttering him up or cheating him, but he didn't trust him. So he wondered if this crown was pure gold. It looked pure gold with maybe precious stones around, but he couldn't tell if it was really some cheap metal just coated with gold. And he just couldn't tell. So he went to his resident brilliant, genius, Archimedes, and say, Archimedes, I want you to figure out whether this is pure gold or if he's cheated me, if he's given me a fraud. Archimedes said, oh, good, I'll grab my knife and just, no. If this is really pure gold, I don't want it harmed or diminished any. I don't want any scratches or scrapes on it. You'll have to do it without damaging it at all, even inside. No, I want it left alone, but I want you to tell me whether it's pure gold or not. Archimedes went home pondering it, thinking about it. And evidently in Greece back then, they had what they called the public baths. Okay, they still have these in some areas of Europe, I think, because you didn't have home plumbing, so they had these places you went. And Archimedes went to take a bath, and he noticed, of course, when he got into the water level rose. He said, wait a minute, I can do that. And his phrase was eureka, meaning I got it. Now, the rest of the story we don't know if really true, but supposedly he jumped out of the tub and went running to tell the king. So excited about his discovery that he forgot to put on any clothes. Now, that's the part we don't know if it really happens, but knowing scientists, I can kind of believe it. Okay? So he went running to tell the king. I'm not sure the king was excited as he was, but so what he did, he could measure the weight of the crown. He could calculate the density of pure gold. He could get his hand on some pure gold and measure its weight, sink it into water, and see how much water it displaced. Okay? But at the same time, keeping it on the scale. And the scale would measure the difference between the displaced fluid and the weight pulling down and the weight of the fluid displaced. And he could do that for the crown, and if the difference was not the same, then it was fake. If it was proportional, then he knew it was pure gold, because gold is very, very dense. Any of the cheaper metals would be less dense, considerably less dense than gold. In fact, if you go back to 9.1, you see how much the difference is. If that cheap metal had been aluminum, gold is 19.3, aluminum is 2.7. He could tell. Iron, 7.89 approximately to 19.3. He could tell. Copper, 8.92 to 19.3. He could tell. Now, even silver is not cheap, but if they had used silver, he could tell, 10.5 to 19.3. Lead, 11.3 to 19.3. Yes, he could tell. The only thing, if it had been platinum, then it would actually be more dense than gold. But platinum is even more expensive than gold. No one would have made the base out of platinum and covered it with gold. Okay, no, not done. Uranium, I don't even know if they really had then. They didn't want that anyway, but that would even be close. So close, maybe he couldn't tell, but no, uranium was really rare, so he wouldn't have been using uranium either. Okay, so yeah, he figured it out. Now, any of you ever gone rafting in a lake, pond? Yeah, okay. What keeps you up? The fact that the raft is less dense than water, so it floats, and hopefully even with your weight on top of it, hopefully it still stays less dense than water. Atlanta, the Chattahoochee River runs sort of right through Atlanta, in one portion of Atlanta. And I went to Georgia Tech as an undergraduate, and there was every spring, Georgia Tech students were just crazy to get out after wintertime and do something crazy. And they had the Great River Raft Race. And you had to create the wackiest kind of raft you could think of, and then hope it made it all the way down the river for that duration. And we took a piece of plywood and drilled holes in it to tie things to, and put milk cartons underneath it, gallon milk cartons. I guess we used some quarts, but mostly gallon. And those were our floating devices, and I think there were 5 or 6 of us on top, and we went down pretty well. A few of our cords, as you hit rapids and stuff like this, some of our gallon jugs got punctured and some of the strings got pulled or broke or something, but we still made it down. I think we probably polluted the river pretty badly with pieces of plastic and stuff, but we didn't think about it back then. But anyway, example 9.6 deals with that. Example 9.7, floating in 2 different fluids. Think saltwater, freshwater. And in fact, boats that do go back and forth, you'll see on the side of the boat what they call the water lines, which is normal and then so much below and so much above. The water line for freshwater will be up here, and the water line for saltwater here, because they float higher in saltwater. So that's basically what that one's dealing with, floating in 2 fluids. It doesn't have to be saltwater, it could be other things too. Okay. Now we move to fluids in motion. And what we call fluids in motion, I went too far. Fluids in motion, streamline flow. Okay? And that's 9.6 in your text. It's called 9.7 here. And streamline flow means that every particle that passes a particular point moves exactly along a smooth path, followed by other particles that pass that earlier. It's also called laminar flow, meaning all the flow is pretty much in one direction. Streamline is the path. Streamline flow is the fact that the particles follow one another. Okay? Different streamlines cannot cross each other. Otherwise, you have something messing up there. The streamline at any point coincides with the direction of the fluid velocity at that point. Okay? Here's the same figure they have, figure 925 in the new book, same as the one in the old slide set. Okay? Streamline flow shown around an auto in a wind tunnel. Now, how they get this to show is they put water vapor or something else that is cloudy in nature out by certain ducts that are separated, and then you can sort of follow the streamlines in. Now, I can remember back when I was young, a lot of times the cars would have blocky windshields and stuff like this, but be very sleek in the back. And I heard someone say, we really should drive that kind of car backwards, because that was terrible aerodynamics this way, pretty good ones that way, but it didn't matter on the backside. This one's much better. Generally, the hood goes up like this. Is a sort of a great sail effect right here. But notice the windshield slopes back. Everything is pretty smooth. That one's going to go through the air pretty well. I don't know if you've ever noticed a Corvette. They don't have this. The lights and everything else are into the structure. In fact, they flip up and down because they do everything they can to minimize that. And most of the sports cars will be like that. This is more of a sedan. You're not going to be driving that. Shouldn't be driving it that fast anyway. So it does have some pretty lousy streamline activity up here. But notice the streamlines, they get closer together and stuff, but they can never cross. Ever. Okay. All right. If you're not flowing in streamline flow or laminar flow, the other option is turbulent flow. The flow becomes irregular. At some point, you exceed a certain velocity, and then you have difficulties. Any condition that causes an abrupt change in velocity is called turbulent flow. Okay? Irregular flow. Eddy currents are a characteristic of turbulent flow. And you've probably seen these. Have you ever done any rowing in a rowboat or something like that? If you have, you'll notice that when you push against the wave, you'll get some of it just moving back, but then some of it curls up and comes around. Just about anything, you'll see that type of stuff. Those are called the eddy currents. The velocity gets so great it can't handle it, and it starts going in circular velocity. Okay. Smoke first moves in laminar flow at the bottom. This is a what did they call these sensors? Sort of incense, something like that you light, and it doesn't really burn in a flame. It just burns enough to produce smoke or incense. And this is laminar flow here. Everything's going along, but suddenly some of these start backing up and curling around. This has gotten into turbulent flow here. Finally over here it does. Over there you can see it has. And then it almost goes to chaotic flow. Everything messing up. And the reason is you have fairly uniform velocity. The heat just rises because warm air rises. But when it gets close to the same temperature, there's not the driving force, and some of it's warmer, some of it's cooler, and so you get irregular velocities, and that creates turbulent flow. Make sense? Now, that was a very short section. Actually, in your text, the new text, they have an equation of continuity here that you deal with this. Actually, there's a couple of things. I'm surprised I'm trying to find out where we have viscosity. Here we go. Okay. Okay. I'm not sure they're going to have this section anywhere. I'm going to hold on for a minute and just flick a few slides here and see if we can find this equation of, here we go. We're going to come back to the viscosity layer. Here's our equation of continuity, okay? Basically, it's this. Now, let's get the terms here right. Let me back up one more. Here we go. No, let's back up again. Sorry. This was in the right order. I just didn't see the term here. Okay. The last paragraph on page 283 under fluid and motion. Here's viscosity. In discussion of fluid flow, viscosity is the degree of internal friction in the fluid. Now, you might say, wait a minute, fluids, those are liquids and gases. Do they have friction? Sure they do. Anything that resists motion is friction. And I think I've given this example before. I can remember doing this as a kid. It was a really dumb thing to do, but I loved doing it. I just got a charge out of doing it. When we were riding down the road, we didn't have, I can't remember how old I was before my family ever bought an air-conditioned car. And we lived in the South too, okay? So we didn't have air conditioning in our vehicle, so we always had the windows down in the summertime. Spring and fall too, you know. Winter was the only time they were up. So the windows were down, and if I was sitting in, I often rode in the window seat because I got car sick easily, and they wanted me near the window, so if I did get car sick, I wouldn't get on anybody else. Okay, so I always had that, and I just got a kick out of putting my hand out the window and feeling, okay. And when you're going along at 25 or 30 miles an hour, not too bad. Going along at 60 miles an hour, I mean, I'm surprised I didn't dislocate his shoulder, you know, because air has internal friction. You can feel it. That's why your arm goes sliding back there. Okay, so viscosity is the degree of internal friction in the fluid. Now, certainly air has very little. I mean, I can do that. I can feel a little bit of resistance, but not a great deal amount. Okay, but if I did this in honey, it would be a lot harder to do. Water is a lot harder to do than air. So viscosity is the degree of internal friction in the fluid that resists the motion. The internal friction is associated with resistance between two adjacent layers of fluid moving relative to each other. So this is talking about fluid to fluid, not your hand to fluid, but fluid to fluid. Okay? And that's also it experiences the same resistance that your hand would. Okay? So, what are some of the characteristics of, say, an ideal fluid? Many features of fluid motion can be understood by considering the behavior of an ideal fluid that satisfies the following conditions. Okay? So these would be an ideal fluid. The fluid is non-viscous. No internal friction between adjacent layers. Never happens, okay? But we can assume that if we could make it happen, that would be an ideal fluid. The fluid is incompressible, okay? In other words, the density is constant. You cannot put any pressure on that and change its volume. If you did, you compressed it. The ideal fluid is incompressible. Believe it or not, most fluids, are close to being incompressible. They will compress a little bit. Gases, that part of fluid, they compress like crazy, okay? And thank goodness they do. So the fluid is incompressible. An ideal fluid would be incompressible. Its density would be constant. You can't make it have a different density. The fluid motion is steady. The velocity, density, and pressure at every point in the fluid do not change with time. That once it's moving, it just stays moving. That has to do with no internal friction. Okay? The fluid moves without turbulence. There is no eddy currents. No eddy currents are present. The elements have zero angular velocity about its center. They all flow in good, straight, laminar flow. Those would be the characteristics of an ideal fluid. They do not exist. Okay? But you can have some fluids that are closer to being ideal than others, certainly in certain ones of these areas. Okay? Now, here's the equation of continuity. Okay, this is 9.6.1 in your text. They don't break it down like that here. AV, A1V1 is equal to A2V2. What in the world are those? Well, A is area. So that would be the area of one pipe times the velocity going through that area is equal to area of another pipe and the velocity going through that. Okay? All right. The product of the cross-sectional area of a pipe and the fluid speed is constant. The speed is high where the pipe is narrow and the speed is low where the pipe has a larger diameter. Have y'all ever experienced that? I can almost guarantee you guys have, and I bet you at least half the girls, if not all of you, have too. Ever been watering flowers for your mom with the hose? My grandmother used to call it the hose pipe. Okay, watering that, and your little brother or sister comes by, and you take your thumb and go, "No, you wouldn't do that, would you?" Okay, or the dog or cat comes by. Okay, what are you doing? The water's coming out when it has a nice big area to come through at a certain velocity, a low velocity. You move your thumb over it, now it has a smaller area, the water has a much higher velocity, and you can spray them. Don't you? No, you didn't do that, I know. Y'all were good folks. Okay? So that illustrates the equation of continuity. The speed is high where the pipe is narrow, the speed is low where it's larger diameter. The product AV is called the flow rate. Okay? Flow rate. A is area, say, let's take square centimeters, centimeters squared. V is velocity, say in centimeters per second. So what have you got if you multiply area times velocity, centimeters per second? Centimeters squared times centimeters, cubic centimeters, that's the volume per second. That's the flow rate, the volume of water per unit time. That's what they measure this at, the flow rate of the air coming out of the ducts. Those people who do this and study it and deal with it, that's usually measured in cubic feet per minute. Cubic feet is area times displacement per minute. That would be your time. Okay, that would be your flow rate. All right. So if you had a small area here and a large velocity here, and then it opened up to a larger area here, what would be true about that velocity? Is it the same, like those arrows almost look like? Standing out half. Well, okay, sorry. If you think about this, the area times the velocity, this volume of air goes, and it's the same as that volume, but this is a shorter distance, so therefore this velocity, displacement per unit time would be less than this one. Now, to me, they haven't drawn those arrows with enough difference. They look too close to the same. This one, in my mind, should be something like that. Okay? that basically is the conservation of mass. You can't get more volume of flow out than what you put in. If you restrict the diameter, it has to go faster. Yeah. Oh my goodness, is it time? Second? Oh, and what were you asking for? Oh, test 6. Okay. Anyone else need test 6? I gave someone earlier. What's that? The lab for Monday? Okay, let me see if I can find that too. Here's test 6. Anyone else need it? Okay, let's see if I can find the lab. Here we go. There's one. There's one. Anyone else need a lab? Oh, you need test 6 too? Oh, that is test 6. Okay. No one else needs a lab. Thanks, I've given all those out to you. Okay, now the first part of that lab, by the way, is from your text. It's just answering short answer questions. The second part was what we did in the lab, and I think you can hear most of that on the recording. All right. All right, so there's the equation of continuity. Goodness gracious. All this grading. Okay. There's a real neat picture here. I wonder if it's going to show here. I don't see it here. But the equation is a consequence of the conservation of mass and a steady flow. If the product of the area times velocity is a constant, then that is equivalent to the fact that the volume of fluid that enters one end of the tube in a given time interval equals the volume of the fluid leaving the other end of the tube at the same interval. Assumes that the fluid is non-compressible, incompressible, and you've got no leaks in the tube. Okay? If it is compressible, then that would change a little bit, but most liquid fluids are close to being incompressible. Gases are not. Okay? Gases are nowhere close to incompressible. So therefore, you can have changes happening there. All right. The picture in your book I was referring to, it was the second half of this figure in your text. It shows a spigot, like in your sink. You've turned on the water just a little bit, okay? And the water comes out. It needs to be nice, slow, laminar flow like this, and as it goes down, it gets smaller. Why is that? Gravity is pulling down, speeding up. Acceleration due to gravity is speeding up, and when it speeds up, the diameter, the area naturally gets smaller. Look at the picture, go home and look at that, try it. You'll notice that happening. You need to have one that the spigot is pretty high off the bottom of the sink to see that. Okay, Niagara Falls, a pretty good example there. Watering a garden, spraying your no, that wasn't it. Okay. Now we move to Bernoulli's equation. And here is Daniel Bernoulli. Now he was, I think, the son of one of the two famous Bernoulli brothers. And he may have had some famous brothers too. There was a whole family of really bright, very bright mathematicians and physicists. Okay? Daniel Bernoulli was one. Now notice when he lived, 1700 to 1782. So that would have been like before Georgia was founded as a colony to just after the Revolutionary War, probably before, while we're still under the Articles of Confederation. So this was early in our history. He was an established mathematician back in Switzerland. And his family were established mathematicians and just brilliant people. They weren't particularly, I don't think, easy to get along with. It sounds like they fought and argued and fussed with each other and competed with each other like crazy. I don't know if it was Daniel, it probably was, that his dad, a very bright, brilliant, famous mathematician and physicist in Switzerland, professor at some university there was a contest going on. And just about every one of these contests, the dad won. I mean, he was just that good. No one else really competed with him much. And he decided to enter this one contest, pretty much sure he was going to win it. Okay? When the results were announced, he found out his son, I think it may have been Daniel, without notifying him, without him even being aware of it, had entered the contest and actually beat the dad. The dad was furious, kicked him out of the house, said, if you can beat me in math, go and make your own living. So I don't know if that's really true or not, but they were quite a family. He wrote a book on hydrodynamics, hydrodynamica. He also did work that was the beginning of the kinetic theory of gases. Brilliant, brilliant scientist. And what we're going to talk about is Bernoulli's equation. Okay? Now, the equation of continuity says that the product of the area times velocity is equal. What Bernoulli's equation does is a consequence of energy conservation as applied to an ideal fluid. Okay? In deriving Bernoulli's equation, we again assume, okay, back up a little bit. Bernoulli's equation relates not areas and velocities, but it relates pressure to speed to velocities and elevation. Okay? Have I done the illustration of this for you? What's going to happen if I blow? Have I done this? Yeah, I thought I had. If I blow on this, what happens? It goes up. If I blow over the top of it, it goes up too. That's a result of Bernoulli's principle, which comes out of his equation comes out of that principle. Okay, relating the fluid speed, the pressure to the fluid speed. Bernoulli's equation is a consequence of conservation of energy applied to an ideal fluid, and it assumes the fluid is incompressible, which most of them are not really, but close, well, somewhat. Non-viscous, all fluids have some viscosity, and flows in a non-turbulent, in other words, laminar, steady state manner. Now, you know, you can easily get out of that too, but if that's the case, then Bernoulli's equation holds. And here's what it does. It states that the sum of the pressure, kinetic energy per unit volume, and potential energy per unit volume has the same value at all points along a streamline. Now let's get that again. The sum of all pressure, kinetic energy per unit volume, and potential energy per unit volume has the same value at all points along the streamline. Now, wait a minute. If you're going to add things together, they better have the same units, right? Let's see if these have the same units. What are typical units for pressure? SI. What would be an SI unit for pressure? Named after Blaise. That's not the UAB mascot, by the way. Blaise Pascal. What is a Pascal? Newton, force per unit area. That's pressure, force per unit area. So that would be newtons per meter squared. Well, if you break down what a newton is a what? Basic units. Kilogram, meter per second squared per meter squared. Okay? So basically it gets down to being kilogram per meter second squared. Okay? Those are the fundamental units of a pressure. Let's see what they are for kinetic energy per unit volume. Okay? Well, this would be kinetic energy is mass per unit volume, 1/2 mv squared. Okay? That is kinetic energy, 1/2 mass times velocity squared. I don't know what I said. That is kinetic energy. Per unit volume would be divide that by V. I mean, yeah, capital V. This is little v, that's capital V. Well, mass divided by volume is density. So that's 1/2 rho V squared. Well, let's break that down. That would be mass, distance squared per volume, which is distance. Oh, wait. Mass in kilograms. Distance squared, meters squared, per second squared, and density is meters cubed. And here the meter squared cancels 2 out of 3 of the meter cubes out. And again, you get kilogram per meter second squared. Yeah, that works. Well, what is potential energy? mgy. Remember that one? mgh, mgy. Okay. Well, if you do per unit volume, that's mass per unit volume, that's density. So mass would be kilograms per meter cubed volume times g, which is distance, meter per second squared, mass per second squared, times y, not mass, meter per second squared times meter. Y would be in meter. So these 2 meters cancels out 2 out of 3 of those, and again you get kilogram meter per second squared. And this says that is a constant. The pressure, which is an imposed applied energy, plus the kinetic energy, plus the potential energy, that's got to be a constant. Okay? That was basically on all points along a streamline. Okay, and the streamline may be moving. Now, that also explains some of this. The pressure I'm doing is the blowing. When I blow on the underneath side, this page has been wrinkled. Okay. If the pressure is greater, then the kinetic energy is increased, potential energy is increased per unit of volume. Okay? When I do this, I'm not adding any pressure to this at all. Okay? I'm increasing the velocity, so therefore the kinetic energy of the air above it, and may change this a little bit, so therefore it increases the pressure below it, and that is your pressure gradient. And you go from there. So that wasn't the best of examples, but go with it. There's Bernoulli's equation. Applications of Bernoulli's equation, let's see. Last time y'all let you go too soon, so I want to make sure I don't do that this time. I think a bunch of you got up to leave early, and I thought it was the end of class, and it wasn't until y'all were all gone and said, no, it's not the end of class. Okay. But we've already lost a bunch of people anyway. So here's Bernoulli's equation. Applications of Bernoulli's principle. Measuring speed. It shows fluid, strange way to start. Shows fluid flowing through a horizontal constricted pipe. Okay? So here you have velocity of a fluid coming in a large opening, but then you neck it down, and the same volume has to go through a smaller, so the velocity increases. Yeah, we saw that back in continuity. But what Bernoulli noticed is the pressure here is greater than the pressure there. And my first reaction was, wait a minute. If it's closer together, going faster, it seems like the pressure should increase. But no, it doesn't. The pressure decreases. And that's what Bernoulli's principle said. The product of that pressure times velocity basically has to equal. Pressure P1 is greater than the pressure P2 because the velocity at 1 is less than the velocity at 2. Okay? The speed changes as the diameter changes. Okay? It can be used to measure the speed of the fluid flow. Okay? Now, how did you do that? Well, if you have a constriction like this, and you can measure pressure on each side, you can then set up a formula to give you what the velocity were. If you knew the velocity coming in, you can calculate the velocity going out. Now, we did this when we were doing radon research in Florida, and we were trying to determine how much air we were evacuating from, say, underneath a slab or a slab on grade house or underneath polyethylene and stuff in a crawl space house, or generally how you're measuring how much fluid you have coming out. If you know the velocity and the area, you can estimate the amount of gas coming out, and that's basically what we did. So we can measure the speed of the fluid flow. Swiftly moving fluids exert less pressure than do slowly moving fluids. Again, it seems intuitively wrong, but it is indeed true. Now there's some very important medical applications for this, okay? Here is one application of Bernoulli's principle. I think this is one I was just describing. It's called a Venturi tube. What you do here, the height is higher in the constricted area of the tube. Okay, right. Let's get a picture here. Here we have air going through this setup here. We have a large diameter tube here, air being forced through it. It reduces to a very small area here and then expands again to a large area there. And you have you're measuring pressure in all three of those areas. Well, the pressure is the least where the airflow is the fastest, so that really pulls it up here. Now, to me, this one look fairly close. It may be this is a little smaller here than that is, and if so, that would pull it up a little bit more, and the biggest one would have the least pressure. Okay, the height is higher in the constricted area of the tube. That indicates that the pressure is lower. Pressure is lower in the narrow part of the tube, so the fluid level is higher. Okay. Any questions on that? So let's consider an object moving through a fluid. All right, before we do that, there's another quick quiz. You observe two helium balloons, okay, floating next to each other at the ends of strings secured to a table. Okay, they're just hanging there by strings. The facing surfaces of the balloons are separated by 1 to 2 centimeters, so pretty close together. Okay? You blow through the opening up between the balloons. What happens to the balloons? A, they move toward each other. B, they move away from each other. Or C, they just hang there at the same 1 to 2 centimeters. What you think? By the way, this is the last one in the chapter. What you think? Okay. If you blow through them, you're increasing the speed of the fluid between them. If you increase the speed, what happens to pressure? Decreases. So therefore, they're pulled together. Okay? Now, I don't know if you've ever experienced this, because it doesn't happen that frequently, but I wonder if you have. What if you and another car are driving along at a reasonable rate of speed, and then you're not that close together, but a little bit close. But there comes a motorcyclist, crazy motorcyclist, and zooms real fast between you. You know what? Have you ever felt what happens? You actually do get a little bit attracted to each other. When I was in the Navy, one time I was on an ammunition ship, and we were replenishing, or at least training to do that. This other vessel, it had some high-powered admiral or something on board, and he was wanting to get back to port as soon as possible. We didn't have that luxury, and since he outranked our captain, he insisted we go this way that was on the way toward the port. Well, that was not with the seas in our favor. And it was pretty rough seas, and yet he wanted to not lose any time going to port. So he had us go this way, and it was hard to control the ships. And this one wave came up in between the ships from behind, and as its velocity came between us, it sucked the two ships closer together. We almost collided. And you do not want to collide in a naval vessel, because the commanding officer loses his job and the officer of the deck loses his job. I was the officer of the deck, and our commanding officer was there on the bridge complaining that he had chosen this route, and as he was complaining, we almost collided. If it wasn't for a really quick-thinking bosun mate, first-class bosun mate, that cut the tension on the rig, we probably would have collided. And it was one scary circumstance. But sometimes if you have those two balloons, you can see them in grocery stores or other stores when they have a bunch of them blown up. See if you get two that are pretty close together, blow in between, and you'll see they come together. Okay? All right. That was that. Now, an object moving through a fluid. This is other applications of fluid dynamics. In this section, let's see, many common phenomena can be explained by Bernoulli's equation, or at least partially so. In general, an object moving through a fluid is acted on by the net upward force as a result of any effect that causes the fluid to change its direction as it flows past an object. That is a complicated and too long of a sentence, okay? But I think it's pretty close to true. Swiftly flowing fluids exert less pressure than slowly moving fluids, okay? Now, I think that all of you will have experienced this if you've driven very much. I hate it when it happens, when this big old transfer truck goes blowing past you at a high rate of speed. Maybe you've just gotten on the expressway or something like this, and he goes zooming past you. You can actually feel it suck your car in behind. and it can be dangerous, okay? The reverse of that, sometimes people that are driving long distance and wanting to save on fuel prices, they draft another vehicle. The other vehicle is moving pretty good. They get in their wake so that they're sort of pulled along by them because of that lower pressure. The trouble is, to get that to be effective, you have to be too close to them. When you're too close to them, you can increase the possibility of an accident. I've known people who tried to draft. Now, any of you NASCAR fans? Me either. Okay. But they have teams of drivers all working for the same people but in different cars, and what they'll do, one will volunteer to go first and let the buddy who's supposed to win the race draft behind them as much as possible. Okay, and other teams will try to draft onto them, and then there's all this trying to keep them from doing that, but yes, keeping the drafting you want to do. If you've ever watched the Olympics, especially I think it's those bicycle races they have, you'll see people try to draft on others. They're getting really close together, going at high rates of speed, and they will do that. And they actually do it to runners too. There's usually one that goes out there and he's the pace setter. He starts going and the others sort of line up behind him because he's hitting all the air resistance and they're drafting along behind him. He will get tired and have to fall back, and then they'll finish the race ahead of him. Have you ever watched geese fly? How do they fly? Generally in a V-shaped pattern. What they're doing is drafting on each other. And sure enough, that lead goose, or gander, whichever it might be, when it tires, it pulls around, goes to the back, and another one pulls up and takes over. They help each other out doing it that way. Okay? So, lots of examples of using Bernoulli's effect, or at least portions of Bernoulli's effect. Okay? Now, there are some others, and I have a feeling some of these. Okay, here's the application of a golf ball. And I've read this many times. I'm still not totally convinced that it's that important, but it must be because they still build them this way. The dimples in a golf ball help move air along its surface. The ball pushes the air down, okay, as it goes. Obviously, the ball, if the air was coming in like this with no interference, all the lines of force were like this. The ball comes along and now pushes the air. It's got to get the air out of its way. The ball pushes the air. Newton's third law tells us that the air must push on the ball. The spinning of the ball travels farther. The spinning ball travels farther than it would if it were not spinning. Okay? The reason for that is it helps push that air out of the way if it's spinning. Okay? That I can kind of buy. I still don't see that big a importance of the dimples. Okay? The stream of air pushing over the, okay, so that's all they did on the golf ball, and again, that argument was not very convincing. I'll take the word for it because all golf balls have them, and I'm sure the golfers do all they can to make it go as far as possible. Okay. However, I'm surprised they didn't use baseball. That's another, to me, a better example. So we may get back to that. Any of you have these spray atomizers for, say, perfume or yeah, you probably used some before. The stream of air passing over the top. Same thing works for is window washing fluids. You put that on the hose. Lots of different applications like that. The stream of air passing over the open tube reduces the pressure in the tube because the air, you do it here, it nozzles it down. And by the way, this is everything to do with all nozzle design. What you're doing with the nozzle is narrowing it down so that the velocity has to be greater. So by nozzling, narrowing this down, the velocity increases. As it increases, the pressure reduces, sucking the liquid out of your perfume bottle or whatever it is, and spraying it into the air. Okay. So the stream of air reduces the pressure. The liquid rises into the airstream. The liquid is then dispersed into a fine spray of droplets as it hits at the top there. Here is the one that's a little scary. Okay? Or one of the ones that's scary. When an artery is constricted as a result of accumulated plaque on the inner walls, and guess what, folks? We are building that every day we live, okay? There's not much way around it. You can minimize it by eating foods that build less plaque, but things like that are high in cholesterol and some of the low-density lipids and stuff like that tend to build the plaque faster than things that are lower in cholesterol and higher in the high-density lipids and things like that. I don't understand the lipids that much, but I know they claim that's true. To maintain a constant flow rate, the blood must travel faster through this area than you would through this area because you're constricted by the plaque. Okay? In order to do that, the blood speed is high enough, the blood pressure is low, and the artery may collapse on itself. And if it does that, then you may have a heart attack or something like that. And that is basically what happens. I thought they were going to talk about the other side of that possibility, and they haven't. Let me go on and hit that. When do most heart attacks occur? Have you ever noticed that? In older people, when do they usually have heart attacks? Say again? No, okay, I didn't mean that. But I mean, what time of day do most heart attacks? Say again? They seem to be the early morning hours. And why is that? Because the blood flows more slowly than you're not pumping as much. And if when you increase velocity, you decrease pressure. When you decrease velocity, you increase pressure. And that could then cause not the best things to happen either, especially in an area that has restricted flow. Okay. So when your blood pressure goes up, it's usually when you're not pumping it as hard. Okay. All right. Application of the airplane wing. This is what I talked about when we did Bernoulli the first time. This is exactly the principle that makes airplanes fly. They shouldn't fly. Not a several ton piece of metal should not be able to take off and go. It just shouldn't happen. But because of this, the airspeed above the wing is greater than the speed below. Now, especially if you were to take this wing and tilt it a little bit more, which most of them are, the speed down here is pretty slow. Up here, the same volume of air has to go a greater distance and get there at the same time, so therefore the speed has to increase. If the speed increases, the pressure decreases, and that gives you what they call lift. Okay? Gravity is pulling down, but if you get enough lift, then it picks you up and goes. Okay? Now you always have some air resistance flow, and that's the drag that we have here, so the net force is in that direction basically. Okay. The air pressure above the wing, the airspeed above the wing is greater than the speed below. The air pressure above the wing is less than the pressure below, especially if you're slowing it down by hitting the bottom side of the wing. Then there is a net upward force that's called lift. The other factors are also involved, like drag and stuff like this. The difference in pressure between the other side and the top of the ring creates that dynamic upward lift. And the faster you go, the greater that difference is. that's why the planes are on that runway picking up speed. I mean, they have those engines cranked to the max to pick up speed as fast as possible so they'll lift off. Now, if you imagine an aircraft carrier, aircraft carriers are much shorter than runways at airports, folks. Much, 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 much shorter. How in the world do they accomplish a real rapid takeoff? You do several things. One thing, you take the aircraft carrier and you head into the wind. Now, you don't go directly in, you aim just a little bit off, okay? There's a reason for that. You'd rather have a little bit of cross flow than direct on, because this can create some instability. So you want a little bit off. I was the commanding officer on an aircraft carrier several times during flight operations, and you're always measuring wind speed, relative wind speed and direction, and increasing ship speed and changing ship direction to maintain that certain good angle at a certain good speed. Do that all the time. I have a little hand device that's used for that. A circular slide wheel, basically. Okay. That's one way. Head the ship into the wind so you create more wind. Okay. Number two, you crank those engines up just as fast as they'll go. They are in, what do they call that? Supercharged mode. I mean, they are blowing blue flames out of the back of those engines, okay? So they can give maximum lift. Now, when they're sitting there on the deck doing that, that is so hot, and the gases coming out of there are so hot, it would fry anybody that's behind that. So they actually have on the deck of the aircraft carriers these plates. They're called jet blast deflectors. They're operated by hydraulics, and they lift up into the air about 45 degrees, maybe not quite that. So the jet blast that hit the thing then deflects straight up, not out, and burn people on the deck. Okay? So you have those. That doesn't help any, but you're burning at maximum speed. And then you also have a catapult. That is a steam-driven thing. It's a hook that goes under, it catches the eye there. They hook it up, and then when they're ready to launch, they have them going full speed. Then they throw that thing off down the deck, and it goes, and even then, the plane dips a little bit. It's going faster than the ship, but it actually dips a little bit. If it wasn't going faster, the ship would plow right into it, but then it picks up and goes. I don't think I ever want to fly an airplane off an aircraft. I've been in one. I've been in one catapult launch and one, but I was a passenger and happy to be a passenger. And it was a little prop plane, so it wasn't really all that much that we had to do anyway. Okay? Enough of those war stories. Okay. Example 912 is lift on an airfoil. It would illustrate some of that we just been talking about. And then applying physics 9.4, sailing upward. When you have a sail and you're trying to advance in the water and how you adjust the sail to make it happen. Then there's home plumbing, applying physics 9.5, home plumbing. Pretty interesting problem there, or illustration there. And now we get into surface tension. Surface tension, capillary action, and viscous fluid flow. Okay? Now, I'm going to talk in terms of water, but all molecules this will do. Water is especially strong this way. Now, every water molecule, what's water made up of? What's its chemical formula? H2O, okay? Now, I can remember early in my chemistry thing thinking you had an H here, an O here, and another H here. That doesn't happen. And here's the reason why. The oxygen is a central molecule there. And oxygen wants to have 8 electrons in its outer shell. Everything wants to have 8 electrons in the outer shell except hydrogen and helium. Everything wants that. Okay? But it only has 6 electrons in its outer shell. So it shares one with one hydrogen, so that gives it one more, and another with another hydrogen, that gives it more. Hydrogen is happy with 2, so it's sharing one with the oxygen and sharing another with oxygen, so it has 2 in its outer shell. It's called covalent bonding. Okay? Now, so oxygen now has 8 pairs of electrons. No, 4 pairs of electrons, 8 electrons in the outer shell. But they come in pairs. Now, if you have a central atom here, and you try to distribute those 4 pairs of electrons evenly, the way you do that is with a tetrahedral structure. That means, picture this, okay, and one set of electrons are going there, one pair is there, one pair is there, and one pair is here. So any way you turn it, you have an equilateral triangle, something pretty close to that. You know, that's the way you distribute those pairs of electrons most efficiently. Now, of course, the ones with the hydrogen will bend a little bit more or less than the other two, but that means that those 2 hydrogens are always adjacent to each other. You can't get 4 in a tetrahedral structure and there is no opposite side. If you got one here, there's 3 down here. If you got one here, there's 3 over here. There's nothing on the opposite side. So therefore, the 2 hydrogens are like this. They're in a pair. So that leaves the oxygen at one end and the other end the 2 hydrogens. Well, the oxygen, since it's got extra electrons, it has the 2 hydrogen electrons floating around it, it becomes slightly negatively charged. Just a little bit. Polar molecule, we say. The hydrogen, because it's sharing its 1 electron with the oxygen, sometimes it has less. So it's slightly positive. The end of the water molecule that has the hydrogen on it is slightly positively charged. Well, then when water molecule, by the way, H2O, oxygen is 16 molecular weight, hydrogen is 1 and 1, so that's 18. A molecule with a molecular weight of 18, any molecule with a molecular weight of 18 should be a gas. That's just so light, okay? But water is a liquid at normal temperatures and pressures because of that strong hydrogen bonding. The hydrogen bonds to another oxygen, this one to another oxygen, the 2 hydrogens, they just stick together, and that's what pulls them together and makes them a liquid rather than a gas. Okay? Now that is happening in 3 dimensions. So this one here has connected to here and here and here and here, being pulled and tightly together. When you get near the surface of the water, some of these that were bonding upward, there's nothing up there to do, so they tend to spread out this way. So now you have stronger bonds on the surface than you have down here because the ones that were up here are now there, so you have a really strong bond there. Okay? That's called surface tension. Have you ever jumped into the pool and landed flat on your stomach? If you have once, you never want to do it again. It's called the belly flop. It's called pain. Okay? It hurts. Because that water, if you're falling from those high diving people, okay, if you've seen the Olympics, when the people are diving from the high dives, notice they always have something disturbing the water underneath. If they let that be perfectly flat, those people would come out with broken bones. But by disturbing the water, you sort of break some of that surface tension. Now, the other thing it does for you, it helps them see the surface better. Because if it was perfectly flat, you hardly see it. It almost is like a mirror. You don't know where you are relative. If it's got a little bit of, so there's 2 reasons they disturb the water. But that's called surface tension. Now, do we do a lab? We haven't done a lab that we fill the container with water, have we? The next lab we do, the one for this chapter, we'll be doing that, and you'll see the effect of that surface tension. Okay? So the net force on molecule A, the one down there, you're being pulled equally in all directions, but the net force on B, no molecules above it, so therefore it's pulled toward the interior of the fluid and along the surface of the fluid, really tightly there. And that's called surface tension. By the way, it's why you can ski. Okay? You ever water skied or seen people water skiing? Why can they do that? Because the surface tension of the water helps them do that. I've actually seen a guy, he could kick off his skis and do it on feet. He's a little nuts, but he could do it. Okay. The net effect of this pull on all the surface molecules is to make the surface of the liquid contract and be really tight there. And they say that when you're coming off the high dive, really high dive, or platform diving, literally almost feels like you're hitting concrete. It's not quite that bad, but almost, especially if that surface is disturbed. It makes the surface area of the liquid as small as possible, that contracting, and the water droplets take on a spherical shape since the sphere has the smallest surface area for a given body. Okay? I'm sorry, that's an example. That's why a drop of water takes on the sphere, because the water molecules try to pull together, and the sphere is the smallest surface area per unit volume. A square or a cube is not. A sphere is. And that's why, now, a lot of water droplets tend to be a little heavy on the bottom and light on the top. That's gravity pulling down. That's what we call a teardrop shape. But without gravity, they make perfect little spheres. And they're pretty close to spheres anyway. In other words, that atomizer, those are little tiny spheres of whatever you're blowing out of that. Okay. Now, can metal float? Okay. You would think not, because metal is denser than water, right? Now, we've already talked about ships and things like this where you have spaces in there that are filled with air. So yeah, they do float. But how about a solid piece of metal? Well, if it's a big enough piece, no, it's not going to. But you can take a needle, which is solid metal, and you can drop it carefully on the surface, and it does indeed float. If you drop it carefully enough and it stays on there. The surface tension of the water is holding it up. Have you seen the water bugs? They skim across the top. Same principle. Certain frogs perfect that too. Surface tension allows the needle to float even though it's denser. The density of steel in the needle is much higher than that of the density of water, but because it's so lightweight, the surface tension does hold it up. The needle actually rests on a small depression of the liquid surface. This is seen from one end of it. The vertical components of the force balance the weight and keep it up. Because you see the surface tension is pushing up this way and pushing up that way, and that's those two forces. These components of forces cancel each other out, and the net force upward equals that, so it floats in the water. Okay. The surface tension equation is this. Surface tension in a film of liquid is defined as the ratio of the magnitude of surface tension force to the length on which the force acts. Boy, what a weird sentence or statement there. So in other words, we say this is a gamma, is the Greek symbol gamma. Gamma is equal to force per unit length. Okay? The unit is Newton per meter. Newton per meter. Now, what else have we seen that had that unit, Newton per meter? Spring constant. But that's a force displacement, and so on. This is not a displacement. This is surface tension force to the length on which the force acts. In terms of energy, any equilibrium configuration of an object is one in which the energy is minimize. Okay? That's sort of a weird statement to be by itself at the bottom two. How do we measure surface tension? Okay? What we have is a calibrated spring of some nature, sort of like the springs we use in the friction thing, a calibrated spring and a wire ring and the film on the water, and you have that sitting in the water, and then you lift that and measure how much force it takes to lift that off the water. The surface tension is trying to hold it down, and the force is pulling it up. Okay, then once you have that, the gamma, which is that's the measure of surface tension, is force per unit length, and you calculate the length of that circular area, whatever that happens to be down there, the force that you measure divided by that length. The 2L, where is 2L? Is due to the force being exerted on the inside and outside of the ring. I don't even see a 2L. What are they talking about? I think what they did, they got it wrong. This is supposed to be 2L. You'll see that in your book. And it's due to the force being exerted on the inside and outside of the ring. Because you see you got forces pulling this way and pulling that way. So it's twice the length of that. So, weird, okay. All right, final notes about surface tension. Surface tension on a liquid decreases with increasing temperature. Why would that be true? The molecules are moving faster, less attractive forces between them, so there's less surface tension. Surface tension can be decreased by adding ingredients called surfactants. What's another name for a surfactant? Soap. When you wash your hands, is soap cleansing your hands? Is soap killing bacteria? Generally not. What soap is doing is making the water more effective at pulling things off, not rejecting them. And it breaks up that surface tension, and then the materials that are polluting or dirtying your clothes or your hands or whatever, they're easier to come off. Detergent is an example of a surfactant. One of the best, the strongest one, is something called, goodness gracious, it's a diphosphate, I think. No, hexametaphosphate. The old Calgon that made water really soft, that means it broke down the surface tension. It was hexametaphosphate, sodium hexametaphosphate. They don't do it anymore because it tends to pollute too badly with phosphate pollution, and it messes up the ecosystem, so they've done away with that. Closer look at the surface of a liquid. I have a feeling that is a good place to stop. We didn't have a break, so I got started late, but that wasn't your fault. So we'll stop at 9.8.1. Okay, we don't have much more to go, a little bit to go. Oh yeah, this is a long chapter. Go at 9.10. 9.10.4. So we do have a bit of ways to go, but hopefully we'll finish the chapter before an hour and a half next time and have 2 hours to spend on the lab. I don't have the lab fully made up, and unfortunately with that hearing coming up, I'm not going to have a lot of time to do it, so I have a feeling we're going to do the lab. I won't have a printed copy, but y'all just write on notebook paper. So be sure to bring paper to class next time, because the lab probably won't be a formal one. I'll have you writing down everything on paper and turning it in. hopefully in an orderly fashion so I can follow it. So, good deal. All right, good deal. We will, yes. No, actually we have class the following Monday too. The 31st. Try to get your papers in next week if possible, and try to get all your other tests and labs turned in if you haven't, because we don't have much time at the end. Last day of class, the 31st, I'll be returning everything to you, meaning I can't accept anything after the 31st.
So you're not going to do the finals?
The final, I'll give you the final, and it will be that off. And it'll probably be the last chapter test. Oh yeah. You got a week from the time we did it, and I'll even give you more time if you need it. Okay. I've got to go get something else to eat out. Had 4 chicken strips. That's all I had for lunch. I had to pound them down. Good deal, thank you.
I don't know if that's what you're asking for on that one, but that's kind of what I was really confused.
Okay. Yeah. All this means in the case of an acceleration, in other words, you have an acceleration, so there's a net force acting on the system, right?
Okay.
Okay, that's second law. The force acting on that object in terms of momentum, not acceleration, would be time rate of change of momentum. Oh, I just recorded that, sorry. Yeah. And remember, that's why I said that's probably how Newton referred to it. Because he talked about quantity of motion. He probably said the time rate of change of quantity of motion. Okay. That's that part. But you'll get partial credit for that.
All right, and that's a blank one that you when we passed those two, and I meant to turn it into you live.
Okay, thanks for returning that. Sometimes the staples stick together. So.
Yeah.